In section 2.2, we are talking about distributions and how we can create density curves and what a normal distribution would be. The learning objectives for this section are to estimate the locations of the median and mean on a density curve, estimate the areas, proportions of values in a normal distribution, find the proportions of z-values in a specified interval or a z-score from a percentile in the standard normal distribution, find the proportion of values in a specified interval or the value that corresponds to a given percentile in any normal distribution, and finally to determine whether a distribution of data is approximately normal from graphical or numerical evidence. In Chapter 1, we developed a kit of graphical and numerical tools for describing distributions. Now we're going to add one more step to this strategy. So when you're asked to explore quantitative data, remember, first, you always need to plot your data. Make a graph, sometimes a dot plot, a stem plot, or a histogram. Look for the overall pattern, remember our SOCs, and calculate a numerical summary to briefly describe the center and the spread. Now we're going to add the fourth steps where sometimes the overall pattern of a large number of observations is so regular that we can describe it by a smooth curve, and this would be a density curve. A density curve is a curve that is always on or above the horizontal axis and has exactly area of 1 underneath it. So a density curve describes the overall pattern of a distribution. The area under the curve and above any intervals of values on the horizontal axis is the proportion of all observations that fall in that interval. So for example, if we take this histogram, this is a histogram of the scores of all 947 7th grade students in Gary, Indiana, on the vocabulary part of the Iowa Test of Basic Skills. It can be described by a smooth curve drawn through the tops of the bars. So if we take this histogram and we draw a smooth curve, this would be the density curve. So it kind of represents a histogram. Notice it's not perfect, but it's pretty close to that smooth bell-shaped curve. So when we're describing density curves, you know that our measures of center and spread apply to density curves as well as to actual sets of observations. So the median of a density curve is the equal areas point. So it's the point where the area is divided in half. So wherever on the curve would divide the shaded region of the entire curve in half. The mean is what we call the balance point. It's where the curve would balance if it was made of solid material. If we could take that curve and balance it, and it was like a solid block figure, where would it balance? The median and mean are the same for a symmetric density curve. They both will be at the center of the curve. The mean of a skewed curve is pulled away from the median in the direction of the long tail. We saw that last section when we were talking about histograms. So if we have density curves, if it's a smooth curve and it is in the middle, the mean and the median are going to be right in the center. If it's skewed at all, notice how the mean pulls away from the median. Notice how the mean is slightly to the right of the median towards the tailed side. So a density curve is an idealized description of the distribution of data. We distinguish between the mean and standard deviation of the density curve and the mean and standard deviation computed from the actual observations. We're now going to use Greek notation. The mean for a density curve is mu, and the standard deviation for a density curve, we use sigma. Normal distributions, a density curve is normal if they have the same shape, symmetric, single-peaked, and bell-shaped. That's what a normal curve looks like. Any specific normal curve is completely described by giving its mean and its standard deviation. Normal distribution is described by a normal density curve. Any particular normal distribution is completely specified by two numbers, the mean and the standard deviation. The mean of a normal distribution is the center of the symmetric normal curve. The standard deviation is the distance from the center to the change of curvature points on either side. This could also be called like the point of inflection. Where does our curve change from concave down, a bowl that's upside down, to concave up? Where does that point happen? That's where the first standard deviation would fall. We abbreviate the normal distribution with mean mu and standard deviation sigma as n, and we put in parentheses the mean, comma, the standard deviation. So why are normal distributions important in statistics? We will use these the entire year. Our year is basically based on these distributions. Normal distributions are good descriptions for some distributions of real data. Normal distributions are good approximations of the results of many kinds of chance outcomes, and many statistical inferences procedures are based on normal distributions. So what is so good about a normal curve? We have this 68, 95, 99.7 rule. Some books call it the empirical rule. And it says that in a normal distribution, with a mean of mu and a standard deviation of sigma, approximately 68% of the observations will fall within one standard deviation. So if this is the mean, 68% of your data points would fall between one standard deviation from the mean, one standard deviation to the left and one standard deviation to the right. Approximately 95% of the data fall within two standard deviations from the mean. And then finally, 99.7% of the data will fall within 3 standard deviations of the mean. All normal distributions are the same if we measure in units of size sigma from the mean mu as center. The standard normal distribution. The standard normal distribution is the normal distribution that uses the mean of 0 and a standard deviation of 1. Remember in the last section we changed to z-scores? If a variable x has any normal distribution with mean mu and standard deviation of sigma, then we can change everything into a standardized variable of z, and then our standard normal distribution would have a mean of 0 and a standard deviation of 1. This is what we'll mainly focus on. We're going to change a lot of our data into a standard normal. In the back of your book, there is a set of tables. We're going to be starting with Table A. So get your textbook out and find Table A in the rear of the book. Table A is a table of areas under the standard normal curve. The table entry for each value z is the area under the curve to the left of z. So, suppose we want to find the proportion of observations from the standard normal distribution that are less than 0.81. So this translates to P, the proportion or the percent, where Z is less than 0.81. When you go to Table A gives you the value of less than. So what you would do is you would take 0.8, that's along the side here, this first row, you find 0.8, and since it's 0.1, then you go to this column where it's 0.01. So this is 0.81. So we would go to our table and find that the proportion is 0.7910, which translates into 79.1%. So in the table, it always gives us the value to the left. It always gives us the value to the left. Make sure you check out the table and see if you understand how they got that value.